Hello everyone. Last time we concluded our discussion of application layer security. So it is a good time to move on to transport layer security. So far actually we talk about our transport layer services like TCP and UDP. But today I will talk about them more. Not because we needed them right now, because then I will talk about SSL and TLS so that we will talk about security there, but I want to talk about more about TCP and UDP because next week I will be talking about attack types. We will need the definitions of UDP and TCP. We should really know how a packet consists of and so on. So let's start. This is a recall actually. Again, as I told you, we already talked a lot about TCP and UDP, but let's start. So transport layer services and protocols, they provide logical communication between application processes running on different hosts, as you have seen in the picture. Transport protocols run in end systems. Sending sites breaks app messages into segments, passes to network layer. Receiving site reassembles segments into messages, passes to the app layer. More than one transport protocol available to apps. In the internet we use TCP and UDP. So two transport layer protocols available to the application layer. TCP is short for Transmission Control Protocol. UDP is User Datagram Protocol. A transport layer protocol is called a segment for TCP and sometimes datagram for UDP. TCP provides reliable data transfer and congestion control. An application using UDP transport can send at any rate it likes. So we already talked about this, but just think about this as a reminder. Okay. So in our book there's an analogy between to show the difference between transport layer and network layer. There's an analogy between a house and this layers. So at the transport layer establishes logical communication between processes, and the network layer establishes logical communication between hosts. So for the analogy, the example is given like that. Two kids in Anne's house sending letters to two kids in Bill's house. So in this case, the hosts are houses. So at the network level, we have houses. Processes are kids, so they are at the transport application layer, and the transport layer will be communicating with them. Letters in envelopes are application messages. Transport protocol is Anne and Bill who demux to in-house siblings. So network layer protocol is the postal service. So at the network layer, the letters are sent to the houses, but inside the house, the transport protocol takes the command and takes the letters and give it to the rightful owner. So these are basic transport layer services. Process-to-process delivery services for applications running on host. Let's start with multiplexing first. So multiplexing occurs like this when somebody sends a TCP message. It consists of gathering data chunks at the source host from different sockets, encapsulating each data chunk with header information to create segments, and passing the segments to the network layer. So this is what happens in multiplexing. But when the receiving side receives this message, the demultiplexing occurs. So it is delivering data in a transport layer segment to the correct application layer interface socket, whether to a TCP socket or a UDP socket. It depends on the type of data you receive. So here's a picture how it occurs. So in the middle we have a sender, and this sender is actually communicating with two different people. So there are two processes here. The blue ones are the processes, P1 and P2. So for both of them we have different sockets are associated. So for instance in this one, P1 is through the socket communicates with the transport layer, and through the network layer this message is sent to here, and at the again transport layer there's a socket number so that the application layer knows which process this message is intended to, and similarly it happens for this one. So multiplexing at sender handle data from multiple sockets, a transport header, later used for demultiplexing, and when the receivers, actually in this picture 3 of them are receivers, they use header info to deliver receive segments to correct sockets. So here's another example here. The transport layer in the middle host must demultiplex segments arriving from the network layer below to either process P1 or P2 above, as you have seen here. This is done by directing the arriving segments data to corresponding process socket. The transport layer in the middle host must also gather outgoing data from these sockets, form transport layer segments, and pass these segments down to the network layer, because this is a two-way communication. So, transport layer multiplexing requires that sockets have unique identifiers. Each transport layer segment is delivered to a unique socket. For this reason, we use actual port number. A port is a 16-bit number, so it is something between 0 to 65,535, which is 1 less than 2 to the 16, as you know. But first ports from 0 to 1023, so 2 to the 10 actually, reserved for well-known applications, for example HTTP and so on. We already talked about a few ports that are known, but you can see a full list on the internet. Other applications are assigned a port number, which would be larger than 1023. So a message appears like this. Source and destination port number fields here are used in the transport layer segment. And there are other header fields here than the application data here. So you use, since these are 16-bit numbers, you use 32 bits for source port and the destination port number. So we already talked about UDP. It is a best effort service. UDP segments may be lost or delivered out of order to the application. This is a connectionless protocol, no handshaking between UDP sender and receiver. Each UDP segment handled independently of others. Why do we use it? It is good for streaming multimedia apps. It is loss tolerant and rate sensitive. But we also use it for the cases like DNS and SNMP. If you require a reliable transfer over UDP, then you have to do it at the application layer. So you have to add reliability at the application layer, and you have to perform application-specific error recovery. So you have to check in which order you received the data, and if you were expecting some part of the data which you didn't receive, you have to ask for it again and so on. You have to do it at the application layer. So this is a picture for the UDP segment header. You have the source port and destination port number. Length, this is in bytes of UDP segment, includes header. You have the checksum, and then you have the payload. No connection establishments. We will talk about this before. This way we don't put an extra delay. It is simple. No connection state at sender and receiver. Small header size. No congestion control. So this is one of the negative parts of UDP, because UDP can blast away as fast as desired, but it's also, if the receiving part doesn't have that much connection, then you would actually, would cause a problem for the receiving side. So a UDP socket can be created within an application. Here is a sample Python code. And automatic or manual assignment of a port number to the socket is performed. This is a transport layer service. Example is this for the UDP, multiplexing and demultiplexing. Suppose that a process in host A with UDP port 19,157 wants to send a chunk of application data to a process in host B with UDP port number 46,428. So host A does this. Transport layer creates a segment that includes the application data, the source port number, like here, the destination port number, as we specified here. Host A's transport layer passes this segment to the network layer. The network layer encapsulates the segment in an IP datagram. The network layer makes a best effort attempt to deliver the segment to host B. Assume that the segment arrives at the receiving host B. Host B's transport layer delivers the segment to its socket identified by port. So here we are doing the demultiplexing. Ports are necessary in addition to IP numbers, because otherwise we cannot know which process actually sending or receiving this data. So A to B segment, the source port number serves as a part of a return address, vice versa for the other way around. So once you are sending your data, you also include your source port because this will be your return address. But if we go to TCP, this is point-to-point, one sender and one receiver, reliable, in-order byte stream, pipelined, TCP congestion and flow control, which, as I told a minute ago, UDP don't have, full duplex data, bidirectional data flow in same connection, it's connection-oriented, handshaking, exchange of control messages, initiates sender, receiver state before data exchange. So we talked about this before. Before sending data, we perform a handshake. It is initiated by the sender. Flow controlled, sender will not overwhelm receiver, unlike UDP. So TCP socket is identified by a 4-tuple, source IP address, source port number, destination IP address, destination port number. The receiving host demultiplexes, so directs the segment to the appropriate socket by using the 4-tuple. So here is a picture how it looks like. Two clients with the same destination port, 80 to a web server application. Here we have our web server, and here are the source and destination ports, IP and source IP and destination IP. So at the transport layer, it is decided which actually process requires this data. And it is determined by all of these four variables, let's say. So we already talked about this picture. In the internet, some protocols use TCP, some use UDP. It is actually depends on what you need. So let's look at the TCP segment structure in a more detailed way. As we already mentioned, there is a source port, destination port, sequence number, and acknowledgement numbers. Here we have some headers, like as you can see, U, A, P, R, S, and F. These are these are explained here. U is for urgent data, generally not used. Actually, egg number validation. P is for push data now, generally not used. And these are connection establishments for setup, tear down commands. Fin is for finishing, SYN is for initiating, and so on. At the checksum, we have internet checksum as in UDP. The sequence number actually counting bytes of data, not segments. Here we actually define receive window. It is the number of bytes receiver willing to accept. There's an upper bound for that. And these are header fields, typically 20 bytes. And we have the application data, which is kind of a variable length. So source and destination ports used for multiplexing and demultiplexing from the upper layer applications. Sequence number, which is 32 bits, and acknowledgement number 32 bits for reliable data transfer. Header length 4 bits. These are generally empty but used for the TCP options if you prefer. 6-bit flag field here. ACK bits identifies validity of the value in the acknowledgement. These three connections setup and tear down. We already talked about this. I think we don't need to talk more. The sequence number of a segment is the byte stream number of the first byte in the segment. So here is an example. A process in host A wants to send a stream of data to a process in host B over a TCP connection. Suppose that the data stream consists of a file consisting of 500,000 bytes. But also assume that MSS, which is maximum segment size, is just 1000 bytes. So you cannot send the whole file as a single segment. And that the first byte of the data stream is numbered 0. So your first data segment is actually starts from here as the 0 byte, and since we have a maximum segment size of 1000 bytes, you have to finish it at 999, and your second data segment starts at the byte 1000 and goes in this way. The sequence numbers for the first, second, and the third segments are 1000, 2000, and 3000. So they are not the number of segments, but they are actually the number of bytes. Host A's TCP segment's acknowledgement number is the sequence number of the next byte host A is expecting from B. Example is this. Suppose that host A received all bytes numbers 0 through 535 from B, and it is about to send a segment to host B. Host A is waiting for byte 536 and all the subsequent bytes in host B's data stream. So host A puts 536 in the acknowledgement number field of the segment it sends to B. Sequence and acknowledgement numbers for a simple telnet application over TCP is pictured here. So user type C, data is C, but the sequence number is 42, the acknowledgement number 79. Host acknowledges the receipt of C, echoes back, and this is also an acknowledgement is sent for this message too, with the sequence number and the acknowledgement number. As you can see, it is increased by 1. So question for this case, host A received the third segment, bytes 900 through 1000, before receiving the second segment, bytes from 536 through the 899. Thus the third segment arrived out of order. So you received the third segment before receiving the second segment. At this point there are two choices. A host do when it receives out of order segments in a TCP connection. A is the receiver immediately discards out of order segments because they cannot receive it later again. Or the second option is the receiver keeps the out of order bytes and waits for the missing bytes to fill in the gaps. So there are pros and cons of both solutions. For the solution A, this leads to a simpler receiver design because it is easier to manage, but B is more efficient in terms of network bandwidth because you don't have to reset the third segment in this example. Let's look at TCP connection management, establishing and closing a TCP connection, and the potential source of vulnerabilities in this case. Establishing a connection, TCP three-way handshake, we already talked about this in the previous weeks. The client side TCP sends a special TCP segment to the server side TCP. This special segment contains no application layer data but one of the flag bits seen in the segment's header. The bit is set to 1 actually, so this is SYN segment. The initial sequence number is randomly chosen. This segment is encapsulated within an IP datagram and sent to the server. A security challenge is how to randomize the initial sequence number. Then the server extracts the TCP SYN segment from the datagram. It sends a connection is granted here. Still no application data is in the segment. This segment is called SYNAC segment. So it's sent now from here. Security issue is as follows. An incomplete three-way handshake makes TCP vulnerable to SYN flooding attacks. So we will talk about it next week. The client receives the SYNAC segment and sends an X segment to the server. The SYN bit of the X segment is 0. This means the connection is established. The X segment may carry client to server data in the segment payload. Next, the client and server host can send segments containing data to each other. So this is how we perform the three-way handshake. But when we want to close the connection, assume that the client decides to close the connection. The client issues a close command by sending a segment with fin equals to 1 here. The server sends an X segment and the fin segment to the client. And then the client sends back an X segment back to the server. Then there is a time wait and the connection is closed because maybe there are some previous messages you haven't received yet. So For the case of the client, this is what happens. And initially there is no connection. Client initiates a connection by sending a SYN. It receives SYN-ACK and sends ACK back. So this way the connection established. Sends the FIN command, waits for this acknowledgement, and the server sends a FIN command, and the client receives it, sends an acknowledgement, and waits for 30 seconds, and the connection is closed. This, for the server side, it is almost the same. Only difference is that the server doesn't initiate it, but creates a listen socket, and here waits for the FIN command and so on. So these are just for the reminder for the TCP and UDP protocols. But we already talked about that both of the methods does not provide any security, because all of the data is sent as a plain text. There is no encryption involved. So this was a problem in the early days of internet, because people, most of the time the websites started to interact with the users, there were problems, because for instance some of the websites allowed you to create username and passwords for some special services, but since there were no security, all of your username and passwords are sent as a plain text using TCP. But anybody listening to the communication this way can capture your username and password. This is still valid for the FTP communication. If you are sending your username and password by the FTP protocol, then anybody can capture your FTP password. So for this case, for instance, you have to use either FTPS or maybe use SSL in an implicit or an explicit way. Some people still don't know it, so they just share their FTP password with everybody on the internet, but they don't know it. So let's move on to SSL and TLS. So previously we talked about secure email, and we talked about how we can provide confidentiality, data integrity, and total authentication to a specific application like secure email. But this time we want to have all of these properties for every TCP communication, let's say. So how cryptography can enhance TCP with security services? Secure Socket Layer SSL is an enhanced version of TCP, and later on, after SSL 3, it is named Transport Layer Security, TLS, and specified in this RFC. Confidentiality, integrity, and server authentication in a shopping scenario. This is an example how we see the SSL, for instance. Bob wants to buy goods from an online store. What do no confidentiality, no integrity, and no server authentication means in this context? No confidentiality means no encryption. An intruder intercepts Bob's order and obtains his payment card info. This still happens, by the way. Some people don't know the difference between HTTP and HTTPS, so they voluntarily give their credit card info to a web page that doesn't have any security at all. No data integrity means an intruder can modify Bob's order. So he can order something, but actually the intruder changes the order. Maybe you wanted to buy one shoe, but you receive 1,000 of them. No server authentication. A fake shopping website can occur, so the intruder can create a similar looking shopping website, and you wouldn't know if you are giving your credit card info to the correct web page or not. So for this reason we use actually HTTPS. This is a frequently used transaction for secure communication. Some web pages actually forces you to use HTTPS. For instance, you cannot connect to Facebook or Twitter by HTTP. It directly moves you to the HTTPS. If you have a web page and you want to do this, for the Apache server you just add a one-line command to your folder and it automatically does this. So it is a simple practice. SSL can be employed by any application that runs over TCP. SSL resides in the application layer, but it is a transport layer protocol from a developer's perspective. So, I mean, even the name is TLS, Transport Layer Security, but it is actually resides in the application layer. But again, virtually for us, it is a transport layer security. So in the picture where you can see where the SSL actually appears. So SSL provides a simple API with sockets, and Application includes SSL classes libraries to employ SSL. Three major phases: handshake, key derivation, data transfer. Here is an example. Assume that Bob and Alice are in a communication session. Assume that Alice has a private public key pair and a certificate that binds her identity to her public key. At the handshake phase, Bob establishes a TCP connection with Alice. Bob verifies that Alice is ready. Bob verifies that Alice is really Alice by checking the certificate from the certificate authority. Bob sends Alice a master secret key. This key will be used by both Alice and Bob to generate all the symmetric keys that they need for the SSL session. So let's look at it in a more detailed way. So Bob sends TCP SYN and receives SYNAC and sends X. So at this point the TCP connection is established. Then after the TCP connection established, Bob sends Alice a hello message, but this is an SSL hello. And if the server supports SSL, then sends the certificate back. Sends its certificate. So once you have the certificate, Bob creates a master secret key, and by checking the certificate, he knows that he is really talking to Alice. Then encrypts this master secret key with Alice's public key. Since Alice has the private key, she decrypts it and obtains this master secret key. So for a simple communication, for instance, if you only needed confidentiality, you can just use this master secret key like an AES key and you can communicate in a private way. But in the SSL we also want integrity, so we will be using message authentication codes, and so we will be needing different keys for that. So from this master secret key we will be generating other keys. So I think I already mentioned this. The master secret will be used only for the current SSL session. Bob encrypts the master secret key with Alice's public key. Yes, I already mentioned this. Yes, we already talked about this. So far we performed the handshake now, and we also transferred the master secret key. Next step is key derivation. This is the second phase. So the master secret MS can be used as the symmetric session key for both encryption and integrity checking. It is safer if Alice and Bob use different keys for encryption and integrity checking. The method is Alice and Bob use the master secret key to generate 4 keys. These 4 keys are 2 of them are for Bob, 2 for Alice, and one of the keys is for encryption. You will be using as a symmetric key encryption algorithm key. The second key is for message authentication codes. You can use something like HMAC or something. So this is why we have 4 keys. Alice creates message M. She concatenates a shared secret S with message M to create M plus S, then calculates the hash of it. This is how we perform the message authentication code, but we already seen a lot of examples and we already talked that HMAC is most of the time the preferred method. Assume that the master secret is divided into 4 parts to generate the 4 keys from the master secret. Recent status: Alice and Bob share 4 session keys generated from the master secret. The 2 encryption keys will be used to encrypt data. The 2 message authentication code keys will be used to verify the integrity of the data. So next step is data transfer. Data stream is broken into records. Assume that each TCP segment encapsulates 1 record. Message authentication code MAC is actually Bob's record data along with the key MB into a hash function. But again, just imagine HMAC during all of these examples. Integrity checking is append the MAC to each record. So you have the record, then the MAC appended to it, then you encrypt both of them. Encryption is done by encryption key of Bob, probably using AES. The encrypted package is passed to TCP for transport over the internet. So it looks good at this point, but there's actually a problem. I don't know if you see the problem in this methodology, or what can an intruder do. And the intruder in this scenario, Trudy, can do this. So assume that he is able to insert, delete, and replace TCP segments in between. Trudy may capture two segments sent by Bob, reverse the order of the segments, then adjust the TCP sequence numbers, since they are not sent in an encrypted way, then sends the two reverse order segments to Alice. Alice's TCP passes the two records to the SSL sublayer. SSL sublayer decrypts the two records and uses the MAC in each record to verify data integrity of the two records. The two records are sent to application layer. So you can see that this example integrity is broken because order of the segments are changed, and the application layer wouldn't recognize this problem. So the solution is using sequence numbers. Bob maintains a sequence number counter. For each SSL record, the counter is incremented as the record is sent. The sequence number is not included in the record itself. It is included in the MAC calculation. So MAC is actually a hash of the data plus message MAC key plus the current sequence number. Alice tracks Bob's sequence numbers. This way the integrity is provided. So let's look at the simplified picture of SSL. This is the record format for a simplified SSL record. So you have the type, version, and the length, but these are not encrypted. You have your data, and then MAC of this data is calculated, and then both of them are encrypted with the symmetric key encryption algorithm. So if you go back to our message authentication codes lecture, as you can see here, what we are doing is MAC then encrypt. As I told you during the lectures, I said that this is what TLS 1.2 does, and this picture is actually for TLS 1.2, but for the TLS 1.3 we are actually using authenticated encryption, not this kind of an encryption. So just think these pictures are valid for TLS 1.2, which actually most of the people are still using, but for the TLS 1.3 we will be talking about authenticated encryption. Type, version, and length are not encrypted. Why? Because type indicates whether the record is a handshake message or a message that contains application data. If you encrypt this, and if it is a handshake, since the other person won't have a decryption key, so they wouldn't be able to communicate. Length used by the SSL at the receiving end to extract the SSL records out of the incoming TCP byte stream. A more complete picture of SSL is as follows. Handshake phase. SSL allows Alice and Bob to agree on the cryptographic algorithms at the beginning of the SSL session. Alice and Bob send nonces to each other to create the 4 session keys. Recall that nonce is a number that is used once, and we are doing this to avoid replay attacks. The method is as follows. The client sends a list of cryptographic algorithms it supports and the client nonce. The server chooses a symmetric algorithm from the list of possible algorithms that is sent. For example, AES for the symmetric key encryption. And they also need to choose a public key algorithm. For instance, RSA with a specific key length is chosen. But as I told you, it should be 2048 bits RSA. Shouldn't be considered as secure at this point. A MAC, message authentication code algorithm, like HMAC, can be chosen. The server sends back to the client its choices, a certificate and the server nonce. The client verifies the certificate, extracts the server's public key, generates a premaster secret that we talked about so far, encrypts this secret key with the server's public key, sends the encrypted PMS to server. Recall that from this secret 4 keys will be generated. The client and server independently compute the master secret from the premaster secret and nonces. The master secret is sliced up to generate the 2 encryption key and the 2 MAC keys. Conclusion, all messages between the client and server are now encrypted and authenticated with MAC. Again, here is a picture, but think this as TLS 1.2. This picture won't be valid for TLS 1.3. So you have the data. It is divided into data fragments. MAC is calculated with the secret key for the MAC, and it is appended at the end. Then this is encrypted, so this is MAC then encrypt algorithm. Then you have a record header at the beginning. So record header contain type, version, and length. Make include sequence number and make key, and the fragments, this part is actually around 16 kilobytes. And the SSL record format is here, 1 byte for content type, 2 bytes for SSL version, 3 bytes for length. Then you have the data and MAC, but all of them are then encrypted. We actually have 2 more steps to this picture. You might think that at this point it is enough and we don't need anything more, but actually we need something more. The client sends the MAC of the concatenation of all the handshake messages it sent and received. You know, at the beginning when they were communicating, the client were actually sending which kind of algorithms it supports, and the server chooses which one to communicate and so on. And the server also sends the MAC of the concatenation of all the handshake messages it sent and received. And why do we need such a precaution? It is to prevent handshake tampering. In the first step, the list of algorithms have to be sent in clear text because you haven't agreed on a key yet, because you don't know which cryptographic algorithms you are going to use. So the intruder may delete strong algorithms from the list, thus enforcing the client to select a weak algorithm. In the final steps, the server and client compare the MACs for an inconsistency. In case of an inconsistency, the connection is terminated. For instance, think about it like this. So you are sending a list of algorithms that you support, but you send DES and AES, and TrueD actually sees this and deletes AES from the list of available algorithms. And since you are only sending DES for the symmetric key encryption, if the server accepts this, actually it shouldn't. I mean, actually in your browser, if you go to settings and say that I'm allowing TLS 1.0 or 1.1 or something, this kind of very old algorithms may be used, but you should never allow such a thing, and because to prevent this kind of attacks. If you say that I'm okay to use this, then you don't have any security at all. So this is just to prevent this kind of an attack. And here is a reminder that why we are using nonces are used to prevent connection replay attacks. So for this reason we are using different nonces for each TCP session. The last step is connection closure. An undesired method of closing a connection: terminate the underlying TCP connection. Bob sends a TCP FIN segment to Alice. Why undesired? Because there is a truncation attack by TrueD. TrueD will close the connection by sending TCP FIN segments to Alice, because we assume that TrueD can insert or delete anything to the communication level. So assume that even if you haven't decided to close the connection, the attacker may send the TCP FIN segments to Alice and close the connection. How do we prevent this? SSL session termination is indicated in the type field of an SSL record. So this way, you can prevent such a truncation attack. So this will be all for this lecture. Next time we will continue with network layer.